as we discussed earlier. So a very important part of this then is to define, people talk about distances and they talk about metrics, these words get used very specifically, but a distance metric has a particular definition, and so if it doesn't satisfy, if your similarity relation or dissimilarity relation or function or coefficient or whatever you're calling it doesn't satisfy these rules, then it is not a distance metric. And someone says, give me a distance metric for something, they mean this. Oh, that's spelled wrong. We'll just fix that spelling there. So what is a distance metric? It satisfies some of the things we feel like it should have, that we've been talking about, right? And they're really quite intuitive, mostly, but they're just very specific. Right, so we'll say we have 2 points that are this far apart, and the distance we're talking about could be any of these. So the first rule says that the point distance between itself and itself is going to be 0, but only if they're actually the same point, right? So remember, x and these are just parameters of some function, right? And this is if and only if, right? That's kind of like logical implication in both directions, if you haven't seen that in a while. So basically, if I'm giving it these 2 points, that's why I wanted to clarify here with the data points. It'd be easier to say my plot here is really saying, give me two dimensions, whether you're talking about x variables or y variables or whatever your dimensions are called. You've got 2 vectors which give you a point in that space. You know about the distance between them, right? So each of these x, y's here are really a multi-dimensional point in some space, right? In my current space here, it's a 2-dimensional space. Let's just say we've got our dimension size is 2 of all the features. Right, so the distance on the same point to itself obviously is 0 if they're the same point. Distances are always positive, so there's no such thing as a negative distance. That wouldn't be very useful. Now, if you have some similarity score or metric that isn't really a distance, but it's kind of defining somehow the similarity or proximity of 2 points, it can be negative if you want it to be, but you could not call it a distance metric then, that's all. Symmetry means that it's going to work in either direction, right? So we want the distance between these 2 points, A and B, is the same as the distance between B and A. We don't care about the direction of it, at least for distance metrics. And then we have this triangle inequality, which is kind of as you expect, that let me undo these ones, get rid of those, which would be that the distance here is less than the sum of the distances of the other 2 sides, right? So it's the largest distance, but actually it doesn't even require that it's the largest distance. It's just that the other 2 distances get there directly, right? And so if there are 3 dimensions, then taking the less direct route will give you a higher distance, right? So this is kind of more general than the Pythagorean theorem or what we usually get out of Euclidean distance, but it just means if you take a side route, it should take more time, or at least not take less time, right? You can't get shorter by going through some side thing. So quantum physics is not consistent with this if you have tunneling, right? So a generalization of this called the Minkowski metric, which defines kind of distance metrics in this form. And this is the form of it here, which I have in another slide. And you'll notice that if you just use k equals 2 here, you get your usual distance on a 2-dimensional space, the Euclidean distance, which is what people intuitively just mean by distance when they say it. We're also going to call this the L2 norm. That's an L because it's linear distance metric with parameter 2. The L1 norm, which will also often get used, is if you use k here. So look at it for a moment and think of what happens if you set k to 1. If you set k to 1 here. And that becomes 1, right? That becomes 1. And now we're just talking about the absolute difference between 2 points and summing them, right? So if we go back to my thing here and saying now, what is the distance between A and B, or let me give you another point so it's more visual. Over here, right, I'll just use L2, right? The L2 distance gives you this. What's the L1 distance? Right, it's the distance, it's the difference between the x coordinates and the y coordinates, right? So it's this distance, right? That's L1, right? So if we have a bunch of points and say we're in, 8-dimensional space, which I can't draw, obviously, 4-dimensional space, right? You'd have to make 3 different turns to get there, whereas the L1, for the L1 distance, but for the L2 distance, you'd still have a straight line in that space. Again, imagine this in 4D. That should be easy. That's a joke. Right? So these are kind of some other ways to define these norms, and we often also call this L1 norm the Manhattan distance. If you think of the island of Manhattan in New York, if you've ever been there, you got the nice park up there, you got Statue of Liberty in the water, and you got the water, and you got the island, but in the middle part, it's all just blocks like this, right? So you're talking about the Manhattan distance. The reason they do that is because to get somewhere in Manhattan, you have to go, in this kind of line with a bunch of right angles, so it's an L1 distance. So there's other forms of this. If we just change k to other things, we get other distances that we might use later on. Chebyshev distance is really like the maximum of any of the features between them, right? So think of what's the largest, in which dimension of your space are your data points furthest apart, and then you just use that. Right? It's kind of like an upper bound on distance, right? And so if you know that you've got all these things about, it could be like, imagine comparing stock portfolios or something, or I don't know if genes would work, but money's good, right? So you have something where you have the features now are your values on all your stocks, and you want the one that tells you their most, the distance between them. You'll say, well, which are the stocks that are most different? Which one's the biggest gap between gains and losses? Chebyshev distance would just give you that, because it'd be essentially the max. And that's equivalent to setting k to infinity. Or you could set it to the minimum one and say how similar they are. But this one is pretty common. So now we have this distance metric that's probably quite familiar and uniform in a sense that, not in any kind of distribution sense, but uniform I mean in the sense that every direction, every dimension is treated equally. So you could also then have a question about when you have the distance between 2 points defined. A question that could arise is that distance significant? Is every aspect of that distance relative, right? Because if we have I'll try to draw a 5-dimensional world here. Well, we'll draw a 3-dimensional world, it'll be a little easier. You have 2 data points, you have some distance between them amongst, each of the 3 directions in this. Are they all equally important, right? Are they all the same scale? What's the variation of them? So if you imagine different distributions, talking about similarity between companies that you're trying to invest in, and figure out whether they're in the same type of company or the same type of performance, and your model here is over everything relevant about the company, right? So one of the dimensions is going to be, how much money they make, And one of the dimensions is going to be how many products they sell. But another dimension might just be like news articles or number of links on their website, right? These things can be completely different magnitudes and orders, and it could be that you only care about certain ranges of the numbers to be meaningful, right? So maybe, the number of links that they have into their website may not be as relevant as like a small change in the dollars, right? So you can imagine each of the dimensions could have a quite different distribution. So the Mahalanobis distance is another way to measure this that accounts for the covariance between the different dimensions of the data. So you can compare the distance between two vectors, between two data points, but you can treat each of those dimensions differently so that the distance in one of those dimensions is more important than another, or that, close has different meanings in different dimensions, which makes sense, right? Features, we've already done normalization of features, but even once you normalize, the distance between them might be very relevant. And if you do this, it's kind of less important to normalize if you're using a distance measure like this. So how does it work? It's expressed in this vector notation. So in the previous one, the distance metric, we have a sum taking the difference between every different point and adding those differences together and squaring them, which is very familiar to us, right? This one is defining it in the notation of using vectors. So if we defined the original Minkowski metric in this way, we would simply have dk xy equals x minus y, where x and y are entire vectors, so we're not indexing them by I, and we'd write it this way. So if this isn't familiar to you, you should go back and review your linear algebra. So if you have a vector x, and sometimes you want to put a vector there just to make sure that we know it's a vector, right? And this would be a bunch of numbers of some length, right? And if we say that we're multiplying this, right? T is the transpose, right? Just in case this hasn't come up anywhere else. I remember this question was asked once in a live lecture, so I might as well refresh. We define, because they're rows, each of these is essentially a data point, your vector, right? So you should think of it as that the original vector is a column of data. And so when you take the transpose, you get a row, and when you take the original one, you get this, right? And 1 by n multiplied by n by 1 gives you 1 by 1, gives you a number, right? And here I'm talking about them being the same vector, but here we have it as x and y, but it doesn't matter. We can say that the transpose is equivalent to saying that you're going to take a sum over all pairs ij and multiply the I and the j values and then sum them together. Right, and we give you the same answer. You're basically going through all the values of I. For number 1 of this, you're multiplying by all the numbers of the second one. For number 2 of this, you multiply by all the numbers of the second one. In this case, we've got two vectors, x and y, and so it really does the summing and multiplication for you automatically to do that. That's just some linear algebra for you. So that's our Minkowski that we had before, right, in that form. But this Mahalanobis now adds a new element. It's got the covariance matrix here, which again gives you a mapping between all the y values and the x values, and you've got some number that represents how correlated they are, right? So if it's 1, then they're completely in sync. If it's 0, there's no relation between them. If it's negative, one goes up, the other one goes down, right? It's covariance matrix. And what does this do? If you think about what that does now, we're saying for every pair of points, we've got a number that tells us how similar those 2 points are, and it allows you to weight the importance of different dimensions along while you're doing this sum. Right? So there's another useful method that can be used for distance. Another way is to interpret it is that it's essentially a multi-dimensional version of distance that takes into account the different scales of each direction. It's when you say, there's other ways to think about it in terms of the standard deviation and the mean of those values, which isn't very intuitive. If you think about that, if the distance were the identity matrix, right? If the covariance were the identity matrix, right, so it's just a bunch of ones and zeros everywhere else, that would mean everything would be perfectly correlated. Every x point would be correlated with every y point, and there'd be no kind of other types of scaling. Then it's equivalent to the Euclidean distance. So one way of thinking of it essentially is that you're talking about Euclidean distances, but you're normalizing it to be in any direction you're talking about, even if it's not along a linear, like an actual dimension, whatever, when you're in that space, the distance between these 2 points is normalized to be in units of the standard deviation, right? So, right, so 2 data points that are at the same standard deviation away from each other, given the covariance structure of the data, will have the same Mahalanobis distance from each other. And so it does take into account the ups and downs of how the distributions go, right? So if you've got some very dense area of the data, a distance in there would be equivalent to one where data points are much further apart. So another way of saying that is that if the covariance matrix is diagonal, then we get the standardized Euclidean distance where we just do the original Minkowski distance sum of points, but we divide all the points by the standard deviation at that location. And so that can be useful if you know that the data covariance structure around your domain is very non-uniform, as I was giving as an example earlier. So another measure, kind of covering out other types of data here. We didn't talk much about ordinal types, and it won't come up a lot. But remember, ordinal types are ranked values, right? So we're saying that we have really just a set of orderings. So you might have a bunch of data points, and you literally would have a column of these ordinals, and the value of it, that's annoying, the value of your thing might be like what rank they are, right? So you know where they are, or they could be really just be a number, but the numbers can be varied across, right? So you could literally have something like 200 and very low numbers and very high numbers, but the only thing that matters is the ordinal amongst this type, and the scale doesn't matter. Like, you don't care about the distance between them, just the order. So if that's the case, then in order to use a lot of the methods that are kind of standard, you have to convert them to something useful. And one way to do that is to take the rank itself and just remap it to the range of those numbers. So if the rank of this, if we have this first, third, seventh values here, and we say, well, whatever is the maximum value, right? So in our case, it's this 7th or a 205th rank. And then you essentially normalize to that, right? Say we're going to come up with a new value that comes up with an interval-based number that is like, how far are you along the way towards the maximum of all the possible ranks, and give you a number there. And then that number will be the one that's used to give you an interval value, right? Because we're taking the actual rank and the total and normalizing it. And then you could use any of those methods for these ranked values. But you'd have to keep in mind then that now you have essentially imposed a scale, right, on these and said, well, now that these points are organized, I'm saying that literally they do have a distance between them. And so if you're ever converting to ordinal, from ordinal to these other data types, you are imposing this, that these are now bigger. You're creating these changes, these scales in the data that weren't really there, right? If it really wasn't relevant before, it's just the order that mattered, now you're adding it. So you have to make sure that if you don't draw conclusions about distances there. And another one, the random grab box of distance metrics that we have here is cosine similarity. And this one is actually really important. It'll come up a lot more in natural language processing when we get there, but it's useful in many ways. The idea here is that rather than using a distance that is something like Euclidean distance, where we're summing up the movement along every linear dimension, you could think of it completely differently, right? You could think of it as an angle, right? So for every data point, right, we've got our however many n-dimensional structure here, and points x, y, and z. You could also consider that from some origin, the origin that we're using for our numbering, there's a vector that goes to that point, and the angle between the vectors could be used to compute that distance between them, right? So that's what the cosine similarity is, and obviously you could use any evaluation of angle to do this. The cosine function, if you hold back to elementary school or high school, wherever you learned it, is just the sum of all the values of those two vectors divided by the normalized sums of them. And again, we can do it in vector notation here like this. And when we think of it that way, like usually we want it because we're using it to compute angles, right? But when we see it this way, it actually seems like it's already almost a distance metric, right? Because it's a dot product between the two vectors, summing them together, and is normalized by the sizes of those vectors, right? And that gives you this cosine. So it's not just for trigonometry, right? It's essentially already in the form of a distance metric that we're familiar with. So it's got these properties, so the value goes from -1 to 1. That's how we can get our sine wave values. And it's got a lot of very useful places that it's used, especially when you have very high dimensional space. It might be that some data points are near each other, and this gives you a better representation of them being near each other in high dimensional space rather than some Minkowski style distance. That's why it's very good in natural language, text, and document processing, because the way that we encode documents or text is very high dimensional. So I think it's also used in genetic data analysis quite a lot because of the same reason. It has some of the properties we talked about earlier about similarity of zeros and differences, right? If any of the vectors have zeros in them, essentially that won't contribute to it, right? Because if you're at the origin for various features, then they won't have it. That just won't contribute to the distance at all, right? And if you actually have binary vectors, so if all the vectors are just ones and zeros, so they're on a unit sphere around the origin, then it's essentially almost similar to one of those methods where we are counting the number of differences and similarities in the vector. And it's kind of like it's been normalized by the size of the vectors. So in this particular example, you'll see sometimes that it gives you different answers than Euclidean would, right? Assuming that you agree these are different. Of course, you could argue based on our angle that maybe it isn't, but assume that the distance between x and y is greater than the Euclidean distance is greater than distance between x and z in actual Euclidean space. In the case of the angle, right, the cosine, this angle phi1 will be less than phi2, right? So if it's important that these 2 points are closer to each other than the other ones, it would give you a completely different answer. That's basically my point. We have some calculations. We have another, if you have a larger dimensional space, so we can't draw it, but we have vectors with 7 dimensions, and those are the data points. So if we haven't seen this before, the norm here just gives you the magnitude of that vector by squaring and taking the square root of them, of all the elements, so just doing it amongst itself, right? So it's only, these are the only ones that have actual numbers, so those are the ones only showing up here. And so these are the norms. I guess it's the L2 norm of these vectors, kind of the magnitude, right? We often call this the magnitude as well, so it's kind of how big it is. And it's the length of that line from the origin to the point. And so those are magnitudes, and then we have to have these pairwise ones for all our calculations. So if we compute the Euclidean one, since we get these points, that x and y are 5 apart, and x and z are 4.6 apart. But when we do the cosine between them, we get a very different value because we're looking at the space and the angle between them. And x and y we get 0.38, and x and z we get 0.08. So the answers can be quite different because obviously 2 points could be very near each other in angle, but very far apart in the space. So that's kind of a very common one to use, but it also gets you to start thinking that, you know, anything that kind of is doing this, combining together the different vectors in a way that lets you have interaction between all the data points in it, all the dimensions, and then is normalizing by something based on all of them, those can all be used to come up with measures of distance.